Okay, last time we talked about how to represent derivatives on a discrete grid using algebraic expressions, and today we're gonna expand on that to the topic which is main topic in our course, is how to solve differential equations using computers. Before we proceed, let's review some theory of differential equations. There are basically two types of differential equations, so-called ordinary differential equations and partial differential equations. So ordinary differential equations, as you probably well know, the equations that have one independent variable. So, for example, we have some equation for, let me take some rate of change of temperature as a function of temperature itself and time. So there is only one, well, in this case it's a full derivative. There is one independent variable, time. And there is partial differential equations that have partial derivatives in them. So it's more than one independent variable. So for example, the rate of change of temperature equals to advection of temperature, let's say in horizontal direction, so we have three independent variables here. It's time, x and y, and some dependent variable like t in this case, and so on. So differential equations have various properties. So first property, is some properties. First is linearity. This is an important property. It's whether or not the equation is linear or not. Linear equations can be solved analytically, many of them, or most of them. But nonlinear equations generally very difficult to solve, almost impossible. Very maybe few cases you can solve them analytically. So that's important property. What's linearity? Linearity means that if you have some operator, some differential operator that acts on some linear combination of two dependent functions like alpha times u plus beta times v, then this is it's true. So then this one is linear equation. So basically it means if you have one solution of differential equation and then another solution of a differential equation, then superposition of those two solutions is also a solution. And for nonlinear equation, differential equation, it is not true. So example of linear equation, and besides those alpha and beta not necessarily constant some numbers. It can be actually functions of some independent variables, but not functions of dependent variables like u and v. So example of linear equation, second derivative of u plus second derivative of v equals to 0. Say here's y squared. This is linear. nonlinear equation is the following. For example, this advection equation with advection of velocity by velocity equals to 0, so-called Berger equation. And this equation is nonlinear. And for this equation, superposition of two solutions is not necessarily a solution of this equation. So another example of linear equation, say x du plus du dx plus x squared plus y squared du dy equals to 0. This is linear equation. Also, another property of equation is of course order, and order is equals to order of the highest derivative in the equation. So order of highest derivative. So this is second order equation, because you see there is second order derivative, second derivative, and here is a first order, and this is first order. And generally order is important because it can tell you how many initial and boundary conditions you need. If it's the derivative of certain independent variable, you have only, say, second order derivative, say in x, then you need two boundary conditions for that. If you have, say, for time, you have only single derivative, say dt, then you have only initial conditions for that equation for time, in time. So that tells you, so order of equation tells you number of boundary conditions. Okay, so also there is a classification of differential equations, and in our field, in meteorology and atmospheric science in general, usually all our equations are no more than second order differential solved not higher than second order differential equations. So that's why it's for us it's important to understand classification of second order differential equations. So if you have general equations written like that, dx and equals to some function of phi x y d phi dx, so first derivatives d phi dy. So so the following classification is applied in this case. So this is basically covers all second order differential equations, including this mixed derivative here. That first case, when b squared minus 4ac greater than 0, then this equation is called hyperbolic. So it's like hyperbolic equation. And an example of that is a wave equation. So this is wave equation. And this is basically an equation that describes propagation of a signal with velocity c. So c, here it should be c squared. C is velocity. And this equation is equivalent to two equations. Equals like that. So this advection equation with two sets of velocities, positive and negative. So you see that the signal can travel right and it can travel left from the initial point. So if you draw it, let's say this is x, this is time. So if you start at this point, you have two sets of lines, so-called characteristics. So these two characteristics that basically show this boundary in time and space where the signal from initial point propagated. So this domain at certain time is where information about this perturbation became known. So this domain is called domain of influence or domain of dependence. And outside this domain of dependence, there is no information available about what's going on at this point, what went on at this point certain time ago. So you see, hyperbolic system has this solution which is actually known only in some vicinity of perturbation because of this advection. So signal propagates with a constant speed c. So for sound, for example, c equals to square root of Cp over Cv, specific heat at constant pressure and constant volume, gas constant times T. So you see that speed of sound depends on temperature only as a square root of temperature. So if temperature is the same, so it does not depend on density, anything like that, it depends on temperature. And fortunately, in meteorology, in our field, speed of sound is not that important thing, but it's important if you solve so-called compressible equations, and in that case, it's actually speed of sound is important not for meteorology, but for stability of your numerical algorithm, and that's what we're gonna talk sometime later when we discuss stability issues. So, but speed of sound, that's basically the main thing that constrained so-called time step in compressible models. So that's a hyperbolic system. So basically it's advection equation. Advection equation, that's hyperbolic equation, and it requires certain numerical methods for this particular type of scheme, type of differential equation. So another type of differential equation is parabolic, which is when b squared minus 4ac equals to 0. This is parabolic. And the example of that is diffusion equation. So second derivative, say, of temperature, first derivative in time, rate of change of time equals to diffusion coefficient, second derivative in space. And that's diffusion equation. That's a typical example of parabolic equation. And parabolic equation, unlike A hyperbolic equation actually doesn't have domain of influence, finite domain of influence. It's actually the solution is available and known everywhere in the domain instantaneously. And you would say that it may be unrealistic, but the thing is that the solution is very quickly decays away from the source. So it looks like, for example, if it's a point source of heat, this is X, this is T. So you would have, and you made some spike there, then sometime later it will be very, so it will make it kind of evolve with time. But it would decay very quickly. So the fact that this solution is actually immediately known here, but the values here are extremely small, and so have no practical significance. So only this kind of solution has practical significance. Okay, so this is diffusion equation. It's parabolic, and it requires different set of numerical methods to deal with this problem, and it has different stability criteria and so on. We're going to talk about that later. And finally, another type of equation that's very common in our field is elliptic. So 3-1 is elliptic, and that's when b squared minus 4ac smaller than 0. And this is elliptic equation. And the example of that, it would be, say, Poisson equation for pressure that often arises when you solve so-called inelastic or incompressible equations. You end up with Poisson equation for pressure that looks like the following in 2 dimensions. So this equation is elliptic. So elliptic equations also don't have domain of influence. Solution is known everywhere instantaneously. But again, because of second derivative, because of nature of second derivatives, the signal decays very quickly with distance from the source. So there is no really practical issue with that. For example, in my model in SAM, it's an elastic model and it's global, and so when something happens at the pole, it immediately is known at the equator. So through this elliptic equation, it's immediately this information propagates to the equator instantaneously. But the amplitude of that signal would be so small that it would have no effect on the solution whatsoever. So even though technically it's infinite domain of influence, but practically speaking, the actual distance that the solution propagates away from some point of disturbance is actually, the solution quickly decays away from that point. So, but this is 3 major types of equations that we're gonna deal in this class. So now let's move to another topic and talk about consistency and stability and what it means for convergence of algebraic equations to true calculus differential equations. So next we're going to talk about consistency of finite difference representation of differential equations. What's consistency? Consistency is basically how do we know, how to make sure that our finite difference representation of equations, differential equations, are actually solving the same problem or approaching solution of the problem that is described by original calculus-based differential equations. So basically what we're trying to answer, if our time step and grid spacing approach 0, so it becomes smaller and smaller, theoretically speaking, our algebra should become calculus. And so that basically we're trying to answer: will it become calculus or not, and how to make sure that our solution is consistent with the original numerical solution is consistent with the original differential equation. So that's what we're going to talk about next, is consistency of finite different equations. So for that, let's the best is just to consider an example. So let's consider advection equation, linear advection equation, which say we advect temperature ddt plus c dt dx equals to 0. So we just transport temperature along x-axis in time. So this is hyperbolic equation, so it has two sets of characteristics. One set is moving to the right with velocity c, and one is moving to the left with velocity minus c. So in this case it's only right movers, because there is plus sign here. So we have this is time, this is space. So initially we have, say, temperature signal look like that, and then we have this set of characteristics, so that at some time, future time, this is time n, this is future time n plus 1 index, so we have superscript for time. So this maximum will become maximum somewhere here. So it will look something like that in the future. We'll move to the right. So we use that fact, this method, the so-called characteristics, and apply it as a method of deriving differential numerical or finite difference analog of our actual differential equation. So let's so for that we do the following. So let's consider our grid, discrete grid. So it has points k minus 1, k plus 1. And we have a constant, let's assume for simplicity, this constant grid stepping delta x. Then we have time, and we have time level n. So this is Tn, and this is time level Tn plus 1. So we have constant, sometimes time step delta t equals to time n plus 1 minus time n, and delta x equals to its constant, it's xk minus xk minus 1, for example, and equals constant for any k. So if we use method of characteristics, then so our characteristics propagate with velocity, our signal propagates with velocity c. So x equals to some initial position plus c times delta t. So this is the distance signal would propagate, c delta t. So our solution here at this grid point, so this one is t k n plus 1, will come, if we follow our characteristic backwards, from this point, t star n. So at level n, it comes from here, and here we will make sure that our time step is such that it will actually be in this interval, within this interval, not outside this interval. Because otherwise, believe me, we may get some unstable solution if we use this interval for our numerical representation. So we will make sure that our time step is such that signal will originate in this point star. And so this is some, so this distance here is equals to delta x. So this distance actually what is traveled by the signal is c delta t. And this distance equals to delta x minus c delta t. So now we can say that in the future solution n plus 1 equals to this t n star. So all it does is just translates solution to the right with speed c. So this is true. So now we need to, because we don't have that grid points are not at the same location as a star in general, we need to interpolate between 2 points. So let's use linear interpolation. So we need to interpolate, and linear interpolation between these two known values of temperature at this point and at this point. So we use linear interpolation, and we covered that in one of the previous lectures. So it's basically just weight, this point times weight based on this interval, plus value in this point times weight based on this interval. So let's write it. So it's equals to tk minus 1n times weight in this interval, which is based on this interval. So it's times delta x minus c delta t divided by interval, the whole interval, delta x. So this one weight plus tkn. Now it's based on this weight. Value in here is based, this is incorrect. So it's this value times weight based on this interval, so it's c delta t divided by delta x. This distance over the whole distance, plus t k based on this interval, so it's delta x minus c delta t divided by delta x. So this is an interpolation statement. So this is basically the scheme. So now let's make so this one is equals to tk minus 1n c delta t delta x plus tk minus tk c delta t delta x. So we can write it as tk n plus 1 minus tk n. We take this tk from here and move to the left hand side, and we divide by delta t. So that way this is approximately the forward in time finite difference representation of derivative in time. So this is forward in time, or two-level scheme, forward in time. So we have only two levels, and this such scheme in time is called Euler scheme. Such approximation in time. So we have this dt equals to, let me equals to minus, just plus c divided c times t k n minus tk minus 1 n divided by delta x equals to 0. So this is also a representation of derivative dt dx forward backward in space. We use points k minus 1, so it's backward in space. Or another name for backward in space for this type of scheme, which is like involves advection equation, is called upstream biased. So you see flow goes this direction, these are points, and we get, in order to get information for this point, we use information k minus 1, so upstream from that grid point. So that's why it's called upstream biased. Biased because it's not symmetrical around this point, so it's biased toward upstream. Upstream biased, and it's first order scheme. And how do we know that? Because we derived that this forward in time schemes are first order accurate. But now we need to show. So this is our scheme that we use to approximate the original problem. So this is our calculus problem, and this is our algebra problem now. So the question is this scheme approximates this guy when delta x and delta t approach 0. In other words, is this finite difference representation consistent with the original differential equation? To answer that, we use Taylor series expansion formally and see if this is actually true. So let's try it. So we have this equation. Let's leave it here. Or maybe I just write it here. So we have, this is our finite difference, so we go from calculus to algebra. Okay, so now let's use Taylor series expansion for this equation. So we will have Taylor series around t k endpoint. So let's do it. So we have n plus 1. So that's like delta t away from this point. So we have tkn plus dt dt delta t plus second derivative delta t square over 2 plus or delta t cube, so other terms, minus tk divided by delta t equals or plus, here we have c, here we have tkn, it's the same, and now we expand this guy, we have minus tkn, now minus second derivative, first derivative, sorry, first derivative, delta t, but now delta t here is negative because it's k minus 1. So this end will propagate in here, so it becomes positive. And now second derivative, and it's t squared, so it's actually minus will remain. Sorry, this is not t, of course, it's dx. I'm sorry. It's delta x here. dx squared, delta x squared over 2. And plus some other terms like O of delta x cube in the expansion, and divided by delta x equals to 0. Okay, so now let's see which terms actually recover this original equation. So tk will cancel here. And here we divide by delta t, we have dt dt plus delta t divided by 2, second derivative of t, plus o delta t squared divided by delta t, plus c. So now here these guys also will disappear, and we have this first derivative, delta x will cancel, so we have dt dx minus delta x divided by 2, second derivative t, respect to dx square, plus o of delta x squared. Okay, so now what we shall do with this. So right now we have the following. If we leave this on the left hand side, these terms plus c dt of dx equals to minus delta t over 2, second derivative of t dt square, minus delta x over 2, second derivative of t dx square. Plus o of delta t square, delta x square. So now, if we let delta x and delta t go to the 0, obviously the right hand side will go away. It will become 0. And we'll recover our equation, from which we conclude that indeed this scheme, this finite difference or algebra representation of calculus or this actual differential equation, partial differential equation, this scheme is consistent with it. This what we actually demonstrated here. This scheme is consistent with this, and the order of truncation order of this representation, finite difference representation, is what? Well, it's a leading terms, so it's delta t, and so we have that it's represented only with some O of delta t and delta x. So the leading truncation error is of the first order. So this scheme is first order accurate in time and first order accurate in space. So which doesn't sound very good. Remember, the higher the order the better, because if we now increase resolution or decrease grid spacing by a factor of 2, our solution error will reduce only also by a factor of 2 at best. And that's not what you want. You want something like, if you had second order truncation error, then if you reduce your, say, grid spacing by a factor of 2, the error would reduce by a factor of 4, and that's what you would like to see. That's much better. So that's kind of problem with this scheme, that it converges to original equation, to actual differential equation relatively slowly when you increase resolution in space and time. And this one is not very good thing. So why it's not very good? What actually causing it? It's the main cause for this kind of, and also let's look at this leading truncation error terms. You see the second derivatives in space and time. What do those terms represent? So we have some diffusion-like term, right? This is second order diffusion, but see, we have kind of negative sign. This scheme would have negative diffusion if you will look only at space derivative in a second derivative in space. You cannot have negative diffusion. But the thing is that actually cancelled by, offset by this term. Second derivative, so it's like diffusion in space. But because this is wave equation, one form of the wave equation, we can actually replace second derivative in time with derivative in space. Let's do it. So we have a second derivative, this is wave equation, so we have second derivative in time equals to first c square plus times second derivative in space. So if we replace it, is that correct? Yeah, I don't like the sign of the thing. I made some mistake with sign. Oh, because it was minus and then I put it to the right hand side, yes. So this term could be actually probably in diffusion, not this guy. So, but now if you replace it, we will get that we actually solving the following equation. That's this is normal equation plus, and the leading term will look like delta x times, and here we forgot to multiply it by c, of course, c, yes, c, minus c square delta t divided by 2, second derivative of t with respect to x square plus O of delta t square delta x square. So we see we have this diffusion coefficient here. This is like diffusion. This is nu. So our new diffusion coefficient equals to this thing, and it should be greater than 0 for to be physically possible, which means that there is actually a constraint on the time step delta t depending on a grid space and delta x. So delta x c minus c square delta t should be greater than 0. Which means from that delta t should be smaller than c delta t divided by delta x. This is stability constraint. So delta t and delta x cannot be arbitrary, even though they can become this scheme is consistent with this as delta t and delta x go to 0, but they cannot go to 0 arbitrary way. They only can go to 0 when this condition is satisfied. So delta t should be smaller than c delta t divided by delta x. What this condition physically means? It means that I erased that previous figure that we had, so n plus 1. So when we consider this k plus 1, k minus 1, we consider this characteristic. So this distance c delta t, this delta x. So this says that this distance that a signal traveled in time step delta t should not be bigger than the distance between two grid points. And indeed, in that case, we would interpolate between 2 points. And if time step were longer, then this characteristic would be like, for example, pointing to this point. That would mean that we would have to, using these two grid points, we would have to extrapolate into this grid point. And the extrapolation, that would create instability. You cannot, for this scheme, you interpolate if you satisfy this condition, and you extrapolate if you don't satisfy this condition. So you see, extrapolation kills this stability of the scheme. So this scheme, if you're not carefully if you're not careful in choosing delta t small enough to satisfy this condition, sorry, this is not. It should be like that. So this guy should be smaller than 1. And this is called CFL Courant Friedrich-Levy stability criterion. We will gonna talk about stability in much more detail when in some future lecture. So this one is just considered this introduction. So basically this scheme is only stable when CFL, or the stability criterion, is satisfied. So the CFL should be, or current number, it's called current number, should be smaller than 1. So you see that if it's not the case, the scheme will blow up. And of course, despite the fact that our delta t and delta x can be as small as we want, if this condition is not satisfied, the scheme will blow up. And of course, the solution will not be consistent with the initial differential equation. So from that, we will make this kind of hypothesis or notion that in order for the scheme to approach or to converge to the solution of differential equation, the actual one, the calculus one, at least 2 things should be true. First, the scheme should be consistent, which means that delta x, when delta x and delta t go to 0, it should approach original equation, but also it should be stable. Because if it's unstable, what kind of consistency you're talking about? So 2 things should be better. And that is called this is called the Lax Equivalence Theorem. So Lax is a guy, mathematician, equivalence theorem that states if the finite FDE, finite difference equation, is consistent, then the stability of the FDE finite difference equation is the necessary and sufficient condition for convergence of FDE to PDE. So basically, consistency plus stability equals convergence. So it's sometimes very difficult to prove that your solution is convergent to truth, that your finite difference or your numerical solution is convergent to true solution, because, well, you don't know it, the true solution. So usually what people do, they increase grid spacing, increase resolution, so reduce grid spacing and see if your solution is changing in any way. So when at some small resolution, solution barely changes, then people say, okay, probably I'm approaching the true solution. But you don't really know that, especially in such chaotic system as fluid dynamics, as fluid flow. So this basically theorem tells you that as long as your scheme is consistent, that is, when delta x, delta t, delta y, delta z approach 0, then you theoretically can show that it approaches your original equation calculus, but it's not sufficient. And also your scheme is stable, so your solution does not blow up when delta, so there is some constraint on time step as a function of spacing, grid spacing in grid spacing. And so if it's stable, then basically it says that it actually guarantees that your numerical solution is converging to your true partial differential equation solution. So this is very useful theorem, Lax theorem. So Lax Equivalence Theorem. So now let's return to our scheme, this upwind biased scheme that we use to solve this differential equation. So as I noted before, in reality, by solving it in this form, we don't solve this equation per se, but we solve diffusion, advection diffusion problem, like that. To the and plus some truncation. But our leading term is a diffusive term, diffusion. So instead of solving this equation, which is pure advection of signal, we also, in addition to advection, we, by using this scheme, actually solve this equation. So we add some diffusion with diffusive coefficient equals to C delta t minus C square delta t divided by 2. So one observation that we could make, that when delta t equals to delta x divided by c, so when our signal goes in time delta t propagate exactly the distance between two grid points, our diffusion coefficient will vanish, and then we will solve actual equation. So we can actually, using this scheme, find the exact solution of this equation using time step equals to this. But of course, in reality, that would be great if your c is constant. But in reality, usually our c is a function. In reality, c is some function of x. Can change, your velocity can change as a function of x. So then you cannot use time step for one grid point, one time step for one grid point, another time step for different grid point, because very soon you will completely mixed up and don't know which solution and which grid point corresponds to which time. So your time step should be 1 for all grid points, and that's why even for some grid points this can be true, for other grid points it may not be true. So I wouldn't bet too much into this possibility. So in general, your nu is always such that this condition is not satisfied and your nu is actually not equal to 0, and it's some positive number. So there is some diffusion, and this is diffuse. That's why this scheme is very diffusive. So if you take initial condition as some kind of, say, spike, very soon it would diffuse in space like diffusion would do to any kind of sharp signal. So this solution would look like, instead of like if it starts like that, then as time goes by, it will be like looking like that. So it will diffuse it. And one of the reasons is, of course, maybe you may ask, maybe the reason because we have such a behavior, because our truncation error is too large, because we use linear interpolation. Maybe we should have used parabolic interpolation, and in that case we would decrease the truncation error, and maybe we would get rid of this diffusion in the first place. Well, actually, if you so basically that's what I'm saying. Let's say that we have, so returning to our diagram, time to space. So we have this point here, which is our t star n, t k n plus 1. This is what we use linear interpolation between these 2 points. What if we use all 3 points and use parabolic interpolation using all these 3 points? What then maybe we solve the problem? Well, I won't repeat the solution here, but it's basically the same thing. But if you do that exercise, you would arrive to the following scheme. So still we have Euler scheme of forward in time for time derivative, and plus C, and here we would have central differences. And that would equal to, and here we would explicitly have the following term, c squared delta t divided by 2, and here is diffusion contribution. So plus truncation error, which is still will be, well, here is going to be t squared delta t delta x squared. So the truncation error in this case, after this term, is going to be second order in time and space, and this thing is of course truncation error is the first order because of this delta t here. So, but you see this scheme is definitely consistent, right? Because if delta t goes to 0, this term will drop out, and we will, if we write this as a Taylor series. So this scheme is still can be shown to be still consistent with the original equation. But what's the role of this term? This term is actually what it does. If you don't have it, you solve it without this term, only using centered differences of second order. to approximate your derivative in space, you would quickly find out if you code it that this scheme would blow up no matter what time step you choose. So this scheme this is, okay, of course, just 2 delta divided by 2 delta x equal to 0. So this scheme, that would be natural, kind of approximate forward in time for using forward in time scheme for time derivative, and centered, more accurate scheme than this backward scheme, centered derivatives in space. Then you would find out that this scheme is consistent. So it's consistent. But it's unconditionally unstable. So this scheme would blow up no matter what time step, no matter what grid spacing you use. This scheme is absolutely unstable, unfortunately. It would be great if it was stable. It's a simple scheme, but it cannot be used. It's unstable. But if you add this term, the role of this term is to cancel this implicit negative diffusion term that would arise if you expand this scheme using Taylor series. And to expand, you will see that the leading term, truncation term, has a form of a diffusion, but with negative diffusivity, and negative diffusivity, that what makes it unstable. So by adding this term to the right hand side, which arises naturally from using parabolic approximation here, so this term, what it does, it offsets that negative diffusion. It just cancels it out, and as a result, scheme becomes stable. So this scheme is stable, but for the same condition that your C delta t divided by delta x should be smaller than 1. But at least there is some delta t you can choose to make this scheme stable, but this scheme will be unconditionally unstable. So this scheme with this added artificial diffusion is called Lax-Equivalence scheme. So this scheme is Lax-Equivalence, or also Crowley 1D scheme. And it used to be quite popular scheme, and still probably is in some older models to use for approximating advection operator. But you need to add this artificial diffusion term to make it stable, because central differences together with earlier scheme again by themselves creates unstable scheme. So to stabilize it, you need this stabilizing term that would make your scheme stable. So you see that sometimes obvious choice for finite difference approximation can be actually wouldn't work because of stability concerns. So this scheme is consistent but unstable, so it wouldn't converge because Lax Equivalence Theorem is not satisfied, and this scheme is consistent and also it's stable for this. If this condition is satisfied, then this scheme will approach or would converge to actual solution of this equation if delta t and delta x approach 0. Okay, that's it for now. See you next time.